Okay, so we want to finish up quadratics, in particular the quadratic formula, and then talk about general polynomials. So the quadratic formula, whenever we have a quadratic equation where the quadratic is given in standard form, and we have it equal to 0, then the solution to this is given by the quadratic formula. So I don't want to go through the derivation of it. Essentially, it comes about by completing the square. So if we go through the completing square process and solving this equation like we did last week, then, and you would have to keep the variables general a, b, and c, then you essentially derive the quadratic formula. I'm going to assume that everyone's seen it, at least somewhere in high school. And so our quadratic formula, the solutions to this equation is going to be opposite of b, negative b, plus or minus square root of b squared minus 4ac all over 2a. Now, when is the quadratic formula useful? So my problem-solving methods, I would always say for solving quadratics, you don't have to follow these. It's just my problem-solving method. I would say try factoring first. And then if it fails, do the quadratic formula. The other method, there's a third method that we did last week, essentially, when we were completing the square. You can complete the square of any polynomial, of any quadratic equation, excuse me, and then solve it like we did solving for the zeros on last week's ICs. But essentially, that's the same method as doing the quadratic formula. And so you would have to do the completing the square first, which is a place where you could make mistakes. And then even in solving it, you could then make additional mistakes. So to try to mitigate mistakes, this is my problem solving method. And that kind of brings about, well, where do the mistakes come in with the quadratic formula? It is much quicker, much more direct. The problem is this square root term. So within the square root term, we have b squared minus 4ac, and then you actually need to simplify this. Particularly for our current classes. Since everything's online and all of our tests and quizzes are multiple choice, all of the answers are going to be simplified answers. So if you're not comfortable simplifying things under a square root, it could be pretty tricky, especially if it factors. For polynomials, for quadratics that factor nicely and usually factor over the integers, well, it's easy to solve those equations once we have it factored and get nice integer or rational solutions. Whereas if there's integer or rational solutions and you use the quadratic formula, well, then you have to make sure you're simplifying the square root correctly. And that's just a common source of error that I've noticed for a lot of pre-calc students. So just be careful with that. Let's do some examples. So let's do something like, let's say 3x squared plus, let's say 10x minus 2 equals 0. And so we want to look to see if it factors first. We would check 3 times 2 gives us that 6. And then we want to look at factors of 6 whose difference is 10. So that negative dictates that I want a difference of the factors. And of course, the 10 dictates what that difference should be. And none of those are going to work. So it doesn't work. We have to go ahead and use our quadratic formula. And our solution is x equals opposite of b, which is negative 10, plus or minus square root of b squared is 100, minus 4 times, or a is 3, c, remember that negative, give us negative 2, all over 2 times 3. And now we just got to simplify it. So we'll have 100. That negative will make it a plus. 4 times 3 times 2 gives us 24. All over 6, which is negative 10 plus or minus square root of 124 all over 6. So keep in mind, there are two answers there. One is negative 10 plus that over 6, negative 10 minus square root of 124 over 6 is the other one. So make sure you're doing both. Of course, we also have to simplify. Sorry, that wasn't on screen. So yeah, negative 10 plus or minus square root of 124 over 6. And we need to simplify. So 124, how does it factor and how do we simplify underneath the square root? The easiest way to do that, let's do our scratch work here over on the side. Let's factor out power of 2. We know that 124 is even, so I can at least factor out a 2. And 2 times 120 should be 60, and then that 4 will give me a 2. So 2 times 62, and it looks like we can factor out another 2, so 2 times 31. 31 is a prime number, so we can't go anymore. And so we have 124 is 2 times 2 times 31, or in other words, it's 4 times 31. You're looking for these perfect squares. So how does it simplify? Negative 10 plus or minus square root of 124 then is going to be square root of 4 times 31, or square root of 4 times square root of 31, or 2 square root of 31. So we'll have negative 10 plus or minus 2 square root of 31 all over 6. And lastly, we want to divide everything by 2. So we can factor out the 2. And of course, factor out a 2 in the denominator. Those will cancel, and we are left with negative 5 plus or minus square root of 31 over 3. Any questions on that? Okay, so let's talk about general polynomials. So a polynomial is a function of the form f of x equals an, x to the n plus an minus 1, x to the n minus 1, plus a1, x plus a0. So it's a function with powers of x multiplied by constants. And these constants, these a sub I, can be any real numbers. So we note that the highest power with a non-zero coefficient We usually write this as an is non-zero, gives the degree of the polynomial. And that is n. So in this case, this is an nth degree polynomial. We've got it written out in just arbitrary mathematics notation, where we use subscripts now to indicate, to index our variables, to index our constants, I should say, because we don't know how many letters there are. It's an arbitrary degree n. So pure examples, explicit examples, I should say. Quadratic functions that we've seen is a polynomial, and this is a degree 2 polynomial. Functions like linear functions, still a polynomial that is of degree 1. So the highest power of x is x to the 1. So polynomials or linear functions are polynomials, degree 1. We can even have constant functions. So if we have h of x is equal to pi, this is a function whose output is always the value pi. What's the highest power of x? Well, there are no x's, which it's implied that it's x to the 0, since x to the 0 is always 1. We call these constant functions, and they have degree 0. And notice that we can use any type of values for the coefficients. We commonly see a lot of integers, but of course, sometimes we see rational numbers as coefficients. We can even have irrational numbers. So any of those kind of combinations, let's do one more, perhaps do a higher degree. We can have pi times x to the 3rd minus 17 x squared plus 2 square root of 2 x to the 15th minus, say 3 over, say 31 x minus e. Or e is Euler's number. We'll get to that later this semester. It's about 2.718, but it's another irrational number. So it doesn't matter. The coefficients don't have to be integers. We like it when they are. They commonly are, but they are not always. They can be irrational numbers. It could be crazy square roots. It could have had cube roots or sixth roots or anything like that. And in this case, notice that I didn't necessarily write it in order. Good practice is to rearrange it. So always write your polynomial if you'd like, with your first line of scratch work, put all the powers of x in descending order. Even if the highest power isn't listed first, this highest power is what dictates the degree of the polynomial. So this is a degree 15. Any questions? Okay, so we want to get into, well, what are these properties of polynomials and how can we graph them? It's kind of our first objective of almost learning any type of function. We want to know, what is its behavior? What does it look like? So let's talk about end behavior. And let me get a new piece of paper. Right here. Let's say one thing. So end behavior I want to do with graphs. So we'll save the next page for writing a bunch of graphs. So our node is just going to be that, the end behavior and when I say end behavior, we mean as x goes to plus or minus infinity. So we want to know what happens as x gets either really big or really small. It goes to far to the right, far to the left. What are the y values doing? What is the function doing? And it's determined by the parity of the degree. And that means even or odd. And the sign of the leading coefficient of an. So plus or minus. So if I didn't mention it, I think I've been using this term. Whenever I say leading coefficient, the leading coefficient is the number multiplied by the highest power of x. So here the leading coefficient is 2 squared root of 2. Here the leading coefficient is 3. Here the leading coefficient is negative 1/2. So the sign, whether it's positive or negative, determines, in some sense, how the graph is flipped, whether it's flipped vertically, up or down, and then the parity determines what's going on at the end. So let's see, let's list all of our cases. So if the degree, let's say degree is even, here, let's use some colors. So if n is even and an is positive, then the graph is going to look like this. At least at the endpoints, both ends are pointing up. That's what we mean by end behavior. We don't know what's going on in the middle. We'll work more on that. I'll probably get to it on Wednesday. Could be a bunch of bumps. We don't know. We don't know how it's looking just from that information. But we do at least know what's going on at positive infinity and negative infinity. So we can write as x goes to plus infinity, the y values also go to positive infinity. And actually here, let's simplify this. Let's say as x goes to plus or minus infinity. So if my x values get really big or really big negative numbers, y values are always going to positive infinity. Our next case if n is even and the leading coefficient is negative, then, well, as we kind of saw last week, it really corresponds to flipping a graph of a positive function. We could factor out that leading coefficient of a negative number, at least a -1 from the leading coefficient, and it would look like an even function, but then with that minus sign multiplied by everything, it's like doing the function transformation that flips us vertically. So it's exactly the opposite. Our endpoints are both pointing downward. And again, crazy stuff could be happening in the middle. It could have a bunch of bumps. It could only have 1 or 2. It could be symmetric, could not be. But the key point is that our endpoints are both pointing downward. So we can write as n, as x goes to plus or minus infinity, y goes to negative infinity. So even degrees, key thing to remember, they're the easiest. Even degrees, both ends point at the same direction. Then all you have to remember is, well, if it's positive, the leading coefficient, positive, both are going to positive infinity. If it's negative, both ends are going negative infinity. If the degree is odd, though, so if n is odd, and let's go ahead and start off with a positive leading coefficient. Odd degree polynomials, the endpoints point in different directions. So one's always going to positive infinity, the other one's going to negative infinity. And with a odd degree and a positive leading coefficient, it is oriented naturally, I guess you could say. Whereas x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to negative infinity. And make up anything that happens in between. We'll figure out how to deal with the in-betweens here on Wednesday. So let's just go ahead and write as x goes to infinity, y goes to infinity. Likewise, negative infinity. I'm just going to put ditto marks. Y goes to negative. And our last case is going to be the flip, vertical flip of that. So if n is odd, and I already used green, didn't I? I'll color code this nicely. If n is odd and n is negative, it just flips. So it looks like this. Endpoints going up that way, and that's going to go down. So something like a cubic with a negative coefficient could be that, or negative fifth degree. And again, let's just write it out as x goes to infinity. I'm going to write arrows. So whenever I have x goes to positive infinity, think of the arrow as x is approaching positive infinity. Y approaches negative infinity. X goes to negative infinity. So my x values get large and negative. Y values are getting large and positive. It goes to positive infinity. Any questions on that? Was it just getting it down? Sure. Sorry. Let me read through the comments here. Let me pull up this page. So just to recap, looks like some people are still taking notes. Our even case, positive leading coefficient, both ends pointing upward. Even degree polynomial, negative coefficient, both ends are pointing downward. And then odd, it always switches. Odd's opposite. So one end goes to positive infinity, one end goes to negative infinity. And you just kind of have to remember when it's odd and leading coefficient's positive, looks like that. Right side's going up, left side's going down. And then the last one here, and it's odd and negative, left side's going up, right side's going